So tail bounds are all about trying to get ideas on how rapidly things converge. And so today I can just give you a first flavor of it, and we'll dive right into this on Monday next week. And it'll be more math. Don't worry. So let's say I want to test out, two different types of Doritos, and I want to find out, whether people like it. Should I launch this product? Should I launch that product? And so I, maybe, put them up somewhere, on the 8th floor of the Gates-Hillman Center, and I see how rapidly those bags disappear, right? And then I can infer from that things like, well, do people like the white or the black design? So here's the math behind it. I have some random variable with a underlying probability measure. And I want to compute things like the expected value of f of x. Okay? And of course, if I have a discrete case, then I have, p of x equals c is just, the sum over all those cases. So this should actually be a sum rather than an integral. Right? And for the moment, I'm assuming that all the xi's are drawn IID from the distribution. So basically, each of the xi's is drawn from the same distribution, and it doesn't matter what their order is. Now I can do things like empirical averages. So, for instance, I can do things like that. The empirical average of f of x is just 1 over n, sum over I equals 1 to n, f of xi. Everybody knows what that is. Everybody's taking an average. Likewise, the empirical estimates for outcomes, so that maybe the outcome is c. I just sum over all those cases I observe xi, and I check whether it equals c, and that's it. So it's very easy. Now, the obvious thing that I want to ask is, well, how accurate is my estimate? How quickly does it converge? So let's say a gambler rolls the dice 100 times. And he's a bit unlucky because the 6 only occurs 11 times. And the fair number would be, 16.7, something like that. So the question is the dice really tainted? Should the gambler be upset? So the first thing I might want to do is I might want to ask, what's the probability of seeing the dice at most 11 times? So by the way, before I do this, why is it a better idea to ask, what's the probability of seeing the dice at most 11 times rather than seeing the dice exactly 11 times? Okay?
Seeing it exactly 11 times would be a very, very small probability. And what you care about is if it should be higher. So you want to incorporate all the probabilities in lower cases as well.
Perfect. So you basically care about the probability in the tail of the distribution. So if this is my distribution of outcomes, of how many times I see it, then what I care is about that entire mass as opposed to just this single location here. And so therefore I basically have to ask, what are the chances that I will get as unlucky as I am right now or even less lucky than that? Because the individual events, especially if I roll the dice many, many times, will have a very small probability, but I care about the entire range. So we can work that out, right? So seeing x less equal than 11 times is I need to sum over I equals 0 to 11 of p of I. And now I can work this out. So I get, I out of 100 times 1/6 to the I times 5/6 to the 100 minus I. Who has never seen that kind of symbol before? Okay, I assume nobody's embarrassed enough to, nobody wants to embarrass themselves enough to admit that they haven't seen it before. But if you actually have not seen it, or if it looks strange to you, go and read your basic combinatorics books, first 2-3 pages. to have that explained to you what it really means. So please do yourself that favor if you've never seen this before. Okay, now in this specific case, I can actually use a computer, right? Because it's a simple for loop. It goes from 0 to 11. It works out those numbers. And we get about 7%. So 7% isn't that great, but, you know, it can happen, so I shouldn't be terribly upset. So let's now go and develop a more general theory for this, in case we cannot just use a computer. So here's an example of how this works in practice. And what I just did is I rolled the dice 1,000 times. And I basically just, computed the average. So that's the blue line. The red line is the average that I should expect. And you can see that for this specific, so the pluses are basically the various observations, whether I get, a 2, a 1, 3, 4, and so on. And so what I'm seeing is that, as I keep on sampling, I will get stuff that actually converges to 1,000. Well, at 1,000, it converges actually quite nicely. Now, the obvious question is, how rapidly does it converge? So basically, is this unusual, and should I typically expect something like this? Or should I expect something that looks more like so? And I just got really lucky. Or, what is a good curve? And does it converge at all? Can we prove that it converges? Because, hey, we can, prove by MATLAB, but that's not really that cool. So these are things that we are going to do next week, next Monday. So we'll basically look at the weak and the strong laws of large numbers. We'll see that actually those curves were quite typical. And this goes like 1 over square root sample size. We'll look at central limit theorem, Slutsky's theorem, delta method, and a lot of math. So buckle up. Next week is math. Okay. So I'm going to be around after this class now until 11. If you have